Welcome, Dr. Roushan. Thank you for your time. You are here at the Quantum Materials 2023 International Conference. I would like to know a little more about Google's work in quantum materials and quantum computing. You have been involved in a series of major breakthroughs in these years in quantum computing at Google's. We even heard about the quantum supremacy of Google. So I would like to ask you what this milestone means for future of computing.
In particular, quantum supremacy or quantum advantage, which happened in the year 2019, is where we defined a task ourselves. In a sense, it was a contrived problem, which we outperform a classical computer because we want to show the power of quantum processors. We want to show what they can do. And we chose a task, quantum processors that we have these years or now are error prone. They have lots of errors in them. So they cannot do any arbitrary task that you like. But if you carefully choose your task, you can show the computation that can be done with quantum processors in these certain tasks can really be superior, can be really advantageous over doing the same computation over a classical computer. So this
give us a number to
number. Well, the algorithm is a moving target. Things evolve. Something that we could do in 2-3 minutes, it would take 10,000 years at that time. Yeah. But then the algorithm, our work inspired people who work on algorithms to do with classical computers to improve their algorithms and inspired people to make better quantum hardware at the same time. So the record moved, and what we claim it takes 10,000 years, now the algorithms get sophisticated, the classical computation, I think now it's about 10-15 hours. But the classical computer, the quantum computer also got better. So again, one is scaling exponentially getting better, another is polynomially getting better. They might cross each other, but eventually the underlying physics is the same. For certain tasks, quantum processors are exponentially advantageous. So we did 53 qubits, now people do about 60 qubits. We said 10,000 years, they'd say 10 hours. Everything is moving and in a sense of improving, but the underlying physics is still the same.
So really the important message is that one is contaminating the other one. I mean,
yeah,
so
I think
together they are developing.
It led to a major intellectual investment and hardware investment, and we are very happy that we inspired this move. I mean, classical numerical simulation techniques have been developed a lot. People are thinking how to make quantum processors better. That leads to conferences that we are in. So we are very happy that we have, provided fuel. I mean, the whole thing was going even without this, but it really inspired the community and brought attention to our work within the bigger science community. Yeah.
Another breakthrough of your research in 2020, you performed the largest chemical simulation on a quantum computer, the largest to date at least. So how has this field evolved since then, and how this accomplishment can really impact material science and also drug development?
I think, again, that's a moving target too. It was the biggest classic quantum simulation of chemistry at that time. I think it was summer of 2020. Okay. Again, it got outperformed by many, including ourselves. So again, it's a moving target. Again, we are figuring out lots of algorithms that do work or do not work. For everything that you see is published and works, there are maybe an order of magnitude larger number of approaches that we find that is not working. So in a sense is again very useful for when others publish and they talk about it and we publish and talk about it, so we see what works and what doesn't work. And this is part of this whole chemistry, is part of the effort to really get to simulate or understand the chemistry, to figure out when you put atoms together what molecules could form and what are the properties of these molecules, which is probably everyone can relate to its application, and it's relevant for material science, or particularly in correlated electron systems for chemistry problems. But I would say still it's in its infancy, because the whole drug industry, these computations that you are mentioning are very advanced. They are about 100 years old in terms of numerical simulations, density functional methods, and all that goes more than a half a century ago. And they are really advanced. So for quantum processors to outperform these supercomputers, we need we need more time, but it's a very good destination to target that we are setting for ourselves.
Right. Here in Quantum Matter, you are in the Industrial Forum, and you have mentioned the importance actually of doing something practical and something on an industrial scale.
Yeah.
Can you tell us about this approach in Google?
Well, in Google, we are mainly, like many major companies, we're mainly focusing on making error-correcting quantum computer. We're trying to make, with the qubits are faulty, so you just cannot make bigger and bigger, so you have to think about to error-correct them as they get bigger. So you have to have active techniques to watch for errors as they come, and then to correct for them. So this is the whole approach that most companies are taking. But then we are focusing on also things that can be done with current qubits. Let's say qubits, I make them better and better. They are 99.5% error, 99.7% error. So they are okay. This was the 2-qubit gates. And then you can say, hey, what kind of problems can I solve with them? So in Google, this research is very, very strong and dominate that we're trying to solve physics problems or address problems that comes in non-equilibrium dynamics, condensed matter physics, that we can address them with our current processors. Yeah.
Okay, I see. So quantum computing is a highly competitive field, we know, so Google, but we have also Microsoft or IBM. So I would like to ask you, what do you believe sets Google's approach apart from the others?
Well, every company has focused on slightly different, or the slightly different model, or a slightly different emphasis. I think we are very close to IBM in terms of approach, and IBM has they want to make an error-correcting quantum computer with superconducting qubits, so do we, and they have a fantastic outreach approach. They emphasize on educating community far better than many other companies. That's really valuable for all of us in US and in the quantum community in general. Google, as I was mentioning, is focusing a little on physics-type problems. We have a dedicated team of people who focus on that, but overall direction is the same. Microsoft is focusing on building a phase of matter which have excitations that are naturally protected, so they want to circumvent this error correction idea by making gates that are very robust. So everyone, which for Microsoft means to go to a different type of platform, different type of research. So everyone is, dealing with mother nature differently and try to find a different approach to it.
So I should ask who has the quantum supremacy now?
Well, I think the record holders, I think, actually are Chinese. So it's none of the companies you mentioned. Okay. I think the current record holder is Chinese. But we are very, but as I was mentioning, what matters is this concept that the computations that can happen with the quantum algorithms on a quantum processor is far superior than when you do it on your classical computer, because the pieces in this quantum processor work based on quantum mechanics, which has superposition and entanglement, and inherently provide opportunity to do advantages over certain algorithms. I have to emphasize this: certain algorithms, so it's not a universal quantum computer yet. Yeah.
I see. You mentioned education, but actually, talking about the other company, IBM, but Google's as well is an open and educational view or approach, let's say. So how do you think this approach is important for fostering a broader community, a broader involvement in this quantum?
Well, very quickly, all of us, or maybe a few years ago, we are noticing that we are running into resources, right? Universities are very good in educating people in traditional condensed matter things, and then maybe educating on quantum information as people go through PhD programs were very rare. Mm-hmm. So with quantum industry growing to this current size, you need really people who are trained properly. And so taking education seriously, it really benefits all of us. So someone has to do a really good job on it. Because when you think about it, this is really the time that we need to engineer quantum systems for sensing, for computation, for communication, for all these purposes. We need people who are properly educated. And the demand is more then you can say, okay, I'm just going to hire people and I'm going to tell them or educate them. You really need people to be educated. And I think the landscape is very slowly changing, and that was totally essentially needed for all of us.
I see. So coming to your path, I read that you were very passionate about physics since you were a child, and now you have a brilliant career at Google. So how did it happen? How was your path?
I cannot deny that luck was a big part of it.
Oh, okay.
So you plan things to some extent, you know, you dream, and but so for some people it happens, for some people they don't get the opportunity. Maybe I was lucky that opportunities lined up, or I could make my way there. I don't know. It's a mixture of being insisting on your.
Yeah. But maybe some choice you made was particularly relevant.
I'm sure in a parallel universe there is another one. I don't know. I mean, you make choices, and I try to make the best out of the opportunities given to me. You know, a few years ago, maybe about when I started at Google, I said, okay, we have these processors. What are they good for in terms of studying physics? I was very much familiar with condensed matter, solid state physics. And then I heard about the word quantum simulation, and I had access to these quantum platforms, and I tried to merge this idea. This was not, of course, my idea. I heard people talking about this. So gradually I could put resources together to have a program that we do this quantum simulation physics at Google.
Oh, excellent. And also very inspiring is your journey from Iran to US, and how this experience really affect you or drive your passion, your work, your way of
when you work on big projects, big science projects, it's not only how much you know, is the knowledge of physics, the knowledge of textbook physics is essential for all of us. If you don't know, you cannot speak the language, right? You have to know what this Schrödinger equation is and all this. That's fine. But when you're working in this big, stressful science project, you're coming from a much bigger collaboration than I am.
Google?
Well, Google is few hundred, you're coming from a few thousand people at CERN. Many other skills in life become important. It's really the art and the balance between when to give up and when not to give up. How far to push, when to choose approach, what you are given resources, and people would listen to you, but now you have to decide what they do with their time. Have they tried enough on some certain area, now they have to stop this. Should I contract this part to a collaborator? Should we do ourselves? So there's lots of human elements, lots of life, how brave you are, how much risk you are taking. So coming from a very unorthodox background, I guess, coming from a different country, living in different continents and all that,
So actually, experience and a diverse background.
Yeah,
is important.
In my work with my team, I realized that this is maybe a bit funny to say, that people who came from little disadvantageous backgrounds are actually perform better under stress.
And more driven.
More driven, and then they can manage failures much better. If someone had all success and everyone had opportunity, when they first hit the first failure in research, they disintegrate. And putting back together and is much harder for them than people who come from less advantageous and sense the hardship and appreciate the resources, as you're saying. So it's an integrated problem. It's not who knows how to drive such and such theorem faster than the others. That takes you only so far.
Yeah.
The others is coming, how do you read between the lines, how do you interact with people, how do you put the projects together, how do you package it, when do you stop, when do you give up, what do you do with your time and people's time. So having different type of jobs before or coming from different backgrounds, it's kind of useful.
Thank you. Your words are very inspiring.
Thank you.
What would you say to a young physicist or a scientist who is starting in the quantum world?
I think, when you think about it, in late 1800s, we got a hold of Maxwell equations. And then for the first part of the century with electric devices, then electronic devices, we really put this Maxwell equation to action. Around the same time, we got the hold of quantum mechanics, right? In 1925, the quantum theory, that the way we are using it is known. For 50 years, we fight with each other over the philosophical implementation of it and philosophical meanings of it, right? And then someone says, okay, stop it. We're not going to settle all these arguments down about the meaning of the quantum theories. So why don't we just put it into some use? And that thing which started or was suggested in early 1980s now is gaining momentum. So I have no doubts that this century would be the century that we engineer quantum the way that we engineer Maxwell equations the last century, right? With electric revolution and then electronic revolution. And now we are seeing that that's really coming to an end, because now we are getting to nanoscales that, quantum mechanics has to be part of it.
Yeah.
So I would say that if they are study hard and they are familiar with quantum, this would be a century of quantum engineers, and we're not going to. So we're going to keep an eye and enjoy the discussion of philosophical meanings of quantum, various interpretations of quantum mechanics. I personally enjoy those conversations, but the engineering is what really is going to be a big deal, and it's not going to die out anytime soon. And I'm guessing is going to dominate the next decades to come.
Okay. Thank you very much. It was a great pleasure.
Sure,
thank you for your time, and enjoy the rest of the conference.
Thank you.
And you stay tuned for more videos.